Hey guys, tonight we're going to explore something you carry with you everywhere. Something so familiar you probably never think about it, and yet it's one of the most ingenious pieces of biological engineering on the planet. Not the social construct, not the politics, just the pure, beautiful biology of melanin and what it actually does for your body every single day. Before we dive in, take a moment to like the video if you're enjoying this kind of content, and subscribe only if you genuinely want more biology to fall asleep to. And let me know in the comments where you're tuning in from and what time it is for you right now. I always love seeing who's joining us from around the world. Now, get comfortable. Maybe adjust your pillow, turn on a fan if you like that gentle white noise, and let's ease into tonight's journey together. Because what you're about to learn might change the way you see yourself. Literally, your skin isn't just covering you, it's protecting you, adapting you, and carrying the story of your ancestors' journey across continents, climates, and thousands of generations. Think about it for a moment. Right now, as you lie there, your skin is performing hundreds of tasks. It's regulating your temperature, sensing the texture of your sheets, keeping water inside your body, and blocking countless threats from entering. But one of its most sophisticated functions, one that took tens of thousands of years to perfect, is something most people never consider. Your skin color isn't random. It's not just genetics in some vague, hand-wavy sense. It's a precise biological response to where your ancestors lived, how much sunlight they encountered, and what their bodies needed to survive. Every shade of human skin, from the deepest brown to the palest cream, exists because of adaptation, real, measurable, evolutionary pressure that shaped your melanin production over countless generations. And here's what's beautiful about it. There's no hierarchy in biology, there's no better or worse, there's only what works where. Your skin color is a solution to a problem, and tonight we're going to explore exactly what problem it solved. So dim the lights, close your eyes if you'd like, and let's begin with the most fundamental question. What is skin color, really? And why does it matter so much more than you ever imagined? Let's start with the basics, because before we can understand why skin color matters, we need to understand what it actually is. And the answer might surprise you. Skin color isn't paint. It's not dye. It's not even really about color in the way you might think. It's about tiny cellular factories buried in your skin, producing a molecule that's been protecting life on Earth for millions of years. That molecule is called melanin. And right now, whether you're aware of it or not, specialized cells in your skin called melanocytes are producing it. These cells sit in the bottom layer of your epidermis, the outermost part of your skin, nestled between the cells that will eventually rise to the surface and flake away. Melanocytes are remarkable little factories. They don't make up much of your skin, maybe 1 in every 10 cells in that basal layer, but their influence is everywhere. Inside each melanocyte is an organelle called a melanosome. Think of it as a tiny leather workshop, stitching together the very substance that gives your skin its shade. These melanosomes produce melanin through a complex chemical process involving an enzyme called tyrosinase, which converts the amino acid tyrosine into melanin. It's a delicate dance of chemistry, one that's been refined over evolutionary time to respond to your environment, your genetics, and even your hormones. But here's where it gets interesting. There isn't just one type of melanin. There are 2 main kinds, and the balance between them determines not just how dark your skin is, but what undertone it has. The first type is called eumelanin. This is the heavy hitter. the molecule responsible for brown and black pigmentation. Melanin is densely packed, highly stable, and incredibly effective at absorbing ultraviolet radiation. If your skin is rich in melanin, it appears darker, ranging from tan to deep brown to nearly black. The second type is pheomelanin. This one's lighter, producing red and yellow tones. Pheomelanin is more common in people with fair skin, and it's particularly concentrated in those with red hair. But here's the catch. Pheomelanin doesn't protect against UV radiation nearly as well as eumelanin does. In fact, when exposed to UV light, pheomelanin can actually generate free radicals, those unstable molecules that damage cells. This is part of why people with very fair skin and red hair have higher rates of sun damage and skin cancer. Their melanin isn't just less protective, it's sometimes actively problematic under intense sun. Now, you might be thinking, okay, so darker skin has more eumelanin, lighter skin has more pheomelanin, simple enough. But it's not quite that straightforward, because skin color isn't binary, it's not black and white, or even brown and pink. It's a continuous spectrum, a gradient that flows across every human population on Earth. The amount of melanin you produce, the ratio of eumelanin to pheomelanin, the size of your melanosomes, how densely they're packed, how they're distributed through your skin layers, all of these factors combine to create your unique shade. Two people who look similar might have completely different underlying melanin structures. Someone from East Asia and someone from Northern Europe might both have relatively light skin, but the type and distribution of their melanin could be entirely different. Someone from West Africa and someone from South India might both have dark skin, but their melanin profiles, shaped by different evolutionary pressures, might tell distinct stories. And here's something most people don't realize. Your skin color isn't static. It changes throughout your life. Babies are often born lighter than they'll eventually become, because melanin production ramps up after birth. Pregnancy can darken skin temporarily due to hormonal shifts. Sun exposure obviously increases melanin production. That's what a tan is. Your melanocytes kicking into overdrive to protect you. And as you age, melanin production can become uneven, leading to age spots, or it can decrease, leading to lighter skin in your later years. Is less than #0. 7# is greater than, but let's zoom out for a moment, because this isn't just about individual cells and molecules. This is about evolution. Every shade of human skin exists because at some point, in some environment, that particular melanin profile helped someone survive long enough to have children. That's it. That's the whole story. Natural selection doesn't care about beauty standards or social hierarchies. It only cares about one question. Does this trait help you pass on your genes? For millions of years, our primate ancestors had dark skin covered in fur. The fur protected them from the sun, so the skin underneath stayed dark, probably as a backup defense, but then something changed. Our ancestors lost most of their body hair, likely as an adaptation for cooling during long-distance running and hunting in the African savanna. Suddenly, that dark skin wasn't hidden anymore. It was exposed, directly facing the sun, and that's when melanin became absolutely critical. Dark skin, rich in eumelanin, became the default setting for early humans. Everyone, and I mean everyone, had dark skin for most of human history. We're talking about hundreds of thousands of years where dark brown to black skin was simply what humans looked like. It wasn't a variation, it was the standard. And it made perfect sense, because humans evolved in Africa, near the equator, where the sun's ultraviolet radiation is strongest. light skin didn't appear until much, much later, and only when humans migrated far enough from the equator that the evolutionary pressures shifted. But we'll get to that journey in just a moment. For now, just sit with this understanding. Your skin color is the result of millions of years of cellular engineering. It's melanocytes responding to ancient sunlight. It's chemistry refined by survival. It's not about race, it's about radiation. And the story of how that color came to be is one of the most fascinating tales in all of human evolution. So let's follow our ancestors as they walked out of Africa and into a world that would slowly, generation by generation, change the very color of their skin. Picture this. Somewhere between 70 and 100,000 years ago, a small group of humans stood at the edge of the African continent, staring across a narrow strait of water. Behind them, endless savanna. Ahead, unknown territory. They had no idea they were about to embark on a journey that would change not just where humans lived, but what humans looked like. This was the beginning of the Great Migration, the moment when our species left its birthplace and scattered across the entire planet. These early migrants didn't leave because they wanted adventure. They left because they had to. Climate shifts, resource competition, population pressure. These forces pushed groups of humans outward into the Middle East, then Asia, then Europe, and eventually across land, bridges into the Americas and island chains into Oceania. It took thousands of years. Generations lived and died knowing only the slow creep northward, eastward, into climates their bodies had never encountered before. And here's what's crucial to understand. Everyone who left Africa had dark skin, deep brown, rich in melanin, perfectly adapted to intense equatorial sunlight. When they arrived in places like Europe or Northern Asia, they still had that dark skin. For a long time, maybe thousands of years, it didn't matter. Dark skin doesn't prevent you from surviving in a place with less sun. It just means you're overprotected, carrying armor you don't necessarily need. But then, gradually, the evolutionary pressure began to shift. And this is where the story gets really interesting, because the evolution of lighter skin wasn't about one thing. It was about a delicate biological balancing act between two critical nutrients, vitamin D and folate. Your body needs both to survive. But the sun, that massive nuclear reactor in the sky, affects them in opposite ways. Too much sun destroys folate. Too little sun means you can't make enough vitamin D, and your skin color is the variable that determines which side of that equation you fall on. Let's start with vitamin D, because this is probably the part of the story you've heard before. Your skin produces vitamin D when ultraviolet B radiation from the sun hits a cholesterol molecule in your skin cells and converts it into vitamin D3, which your body then processes into its active form. This vitamin is essential. It regulates calcium absorption, builds strong bones, supports your immune system, and even influences your mood. Without enough vitamin D, children develop rickets, a painful condition where bones soften and bend. Adults develop osteomalacia, weak and aching bones. Pregnant women face complications. Your immune system falters. Now, here's the problem. Dark skin produces vitamin D much more slowly than light skin. The heavy concentration of melanin absorbs and scatters UV radiation before it can convert that cholesterol molecule. It's incredibly effective sun protection, but it comes at a cost. In Africa, near the equator, this wasn't a problem. There's so much intense sunlight year-round that even dark-skinned people produce plenty of vitamin D. But when humans migrated to Northern Europe, Northern Asia, places where winter days are short and the sun sits low on the horizon for half the year, Suddenly, dark skin became a liability. Imagine living in Scandinavia 30,000 years ago. The sun barely rises above the horizon in winter. When it does appear, it's weak, filtered through clouds, hitting your skin at a shallow angle. You're also covered in animal furs because it's freezing. Your dark skin is blocking what little UV radiation manages to reach you. Over time, over many generations, people with slightly lighter skin, people who could produce vitamin D more efficiently in low-light conditions, had an advantage. They had stronger bones, healthier children, better immune systems. They survived winters better, lived longer, had more offspring. And so, slowly, across thousands and thousands of years, the populations living in northern latitudes became lighter. Not because light skin is inherently better, but because in that specific environment it solved a specific problem. Natural selection doesn't care about beauty or preference. It only amplifies traits that improve survival and reproduction. Light skin in Northern Europe was an adaptation as elegant and necessary as dark skin in equatorial Africa. But remember, I mentioned 2 nutrients. Vitamin D is only half the story. The other half is folate, and this is where the genius of dark skin becomes even clearer. Folate, also called vitamin B9, is absolutely essential for life. It's involved in DNA synthesis, cell division, red blood cell production, and, critically, fetal development. During pregnancy, folate is required for the neural tube to close properly in the developing embryo. Without enough folate, babies can be born with devastating defects like spina bifida or anencephaly, conditions that are often fatal or severely disabling. And here's the kicker. Ultraviolet radiation destroys folate. Intense sun exposure breaks down folate circulating in your bloodstream. Studies have shown that just 1 hour of strong sunlight can reduce folate levels significantly in people with light skin. Now think about what that means. In equatorial Africa, where the sun is relentless, where UV radiation pounds down every single day, losing folate isn't just inconvenient, it's life-threatening, especially for women of childbearing age. Dark skin protects folate. The melanin acts as a shield, absorbing UV radiation before it can penetrate deep enough to destroy folate in the blood vessels beneath. This means that people with dark skin, living near the equator, maintain healthy folate levels even with constant sun exposure. Their children are born healthy. Neural tubes close properly. DNA replicates without error. This isn't a minor advantage. This is the difference between viable offspring and reproductive failure. So now you can see the equation. In high UV environments near the equator, folate protection is critical and vitamin D production is easy. Dark skin wins. In low UV environments, far from the equator, vitamin D production is difficult, and folate destruction is minimal. Light skin wins. It's not about better or worse. It's about fit. It's about matching your biology to your environment. And this didn't happen just once. This is one of the most beautiful parts of the story. Light skin evolved independently in multiple populations. Europeans developed light skin through one set of genetic mutations. East Asians developed it through different mutations. These populations were separated by thousands of miles and thousands of years, yet they arrived at similar solutions because they faced similar problems. Convergent evolution. It's called different paths to the same functional outcome. The genes involved have names like SLC24A5, which influences skin, hair, and eye color in Europeans, or OCA2, which affects pigmentation across multiple populations. These mutations didn't create light skin overnight. They accumulated gradually, spreading through populations because they offered a survival advantage in specific environments. One generation slightly lighter than the last, repeated across 10,000 years. And so, by the time humans had spread across every continent, we looked remarkably different from one another. Not because we were different species. We're all still the same species, interfertile, genetically nearly identical, but because we'd adapted to different slices of the sun's spectrum. The story of skin color is a story of migration, adaptation, and survival. It's your ancestors written on your body. And now that we understand how we got here, let's explore exactly what all that melanin is actually doing for you, starting with the incredible shield that dark skin provides. If you were designing a protective shield for human skin, what would you want it to do? You'd want it to block harmful radiation without blocking visible light. You'd want it to be flexible, self-repairing, and constantly active. You'd want it to adjust its strength based on threat level. And ideally, you'd want it to be built into the skin itself, requiring no maintenance, no thought, no conscious effort. Well, congratulations. If you have dark skin, you're already wearing one of nature's most sophisticated defense systems. Melanin, particularly eumelanin, the type abundant in darker skin, is a biological sunscreen. But calling it sunscreen almost undersells what it actually does. Synthetic sunscreen sits on top of your skin and absorbs or reflects UV radiation. Melanin is woven into your skin cells, positioned precisely where it needs to be, forming a protective cap over the nucleus of each cell like a tiny umbrella shielding your DNA from harm. Let's talk about what it's protecting you from. Sunlight isn't just one thing. It's a spectrum of electromagnetic radiation, and the part that concerns us most is ultraviolet radiation. UV radiation comes in 3 types: UVA, UVB, and UVC. UVC is almost entirely blocked by Earth's atmosphere, so we don't worry about it much. UVB is the stuff that causes sunburns, and it's also what your skin uses to produce vitamin D. UVA penetrates deeper into the skin and contributes to aging and long-term damage. Both UVA and UVB can damage the DNA inside your skin cells. When a photon of UV light strikes a DNA molecule, it can cause mutations, errors in the genetic code. Most of the time, your cells catch these errors and repair them. Your body has elaborate DNA repair mechanisms running constantly, scanning for damage and fixing it before it becomes a problem. But sometimes, a mutation slips through, and if that mutation happens in a gene that controls cell growth, you've got the beginning of cancer. This is where melanin becomes your silent guardian. Eumelanin absorbs UV radiation across a broad spectrum. It's not perfectly efficient, nothing in biology is, but it's remarkably good. Studies suggest that dark skin provides a natural sun protection factor of around 13 to 15. That means if it would take 10 minutes for unprotected light skin to burn, it would take roughly 2.5 hours for dark skin under the same conditions. But the protection goes deeper than just preventing sunburn. Dark skin dramatically reduces the risk of all forms of skin cancer. Melanoma, the deadliest type, is about 20 times less common in black individuals compared to white individuals. Basal cell carcinoma and squamous cell carcinoma, the more common but less aggressive forms, are also significantly rarer. The melanin is literally intercepting the radiation before it can cause the DNA damage that leads to cancerous mutations. And this isn't just a modern concern. This has been the reality for hundreds of thousands of years. Imagine being an early human living on the African savanna. You're outside all day, every day. There's no shade except the occasional acacia tree. No hats, no clothing covering your arms and face, at least not in the earliest periods. The sun is directly overhead for much of the year, meaning UV radiation is hitting you at its most intense angle. Without dark skin, your DNA would be under constant assault. Skin cancers would appear earlier and more frequently. Some might be disfiguring, some might be fatal, but even non-fatal cancers could reduce your ability to hunt, gather, or care for children. In evolutionary terms, anything that reduces your reproductive success gets selected against. So dark skin wasn't just helpful, it was essential. It was the difference between a functional life and a body slowly breaking down under the sun's relentless radiation. And natural selection strongly favored individuals with more melanin, generation after generation, until dark skin became the universal human trait for most of our history as a species. But melanin doesn't just block radiation, it also neutralizes free radicals. When UV light does penetrate into your skin, it can create reactive oxygen species, unstable molecules that bounce around, causing damage to cell membranes, proteins, and DNA. Melanin acts as an antioxidant, absorbing these free radicals and rendering them harmless. It's a two-layer defense system. First, block the radiation. Second, clean up whatever gets through. There's another advantage that's often overlooked. Dark skin ages more slowly, at least in visible ways. Wrinkles, age spots, sagging, these are largely caused by cumulative UV damage to collagen and elastin, the proteins that keep your skin firm and elastic. Because dark skin blocks more UV radiation over a lifetime, it experiences less photodamage. The result is that people with darker skin often look younger than their light-skinned peers at the same age, not because of genetics unrelated to skin color, but specifically because their melanin has been protecting their collagen for decades. This isn't vanity. In evolutionary terms, looking healthy and vigorous has reproductive advantages, but more importantly, the same processes that cause visible aging are also happening invisibly at the cellular level. Less UV damage means healthier cells, more efficient repair mechanisms, and a lower cumulative burden of mutations. It's like the difference between a car that's been parked in a garage versus one that's been left in the desert sun for 20 years. Both cars are the same age, but one has been protected, and it shows. Now, does this mean dark skin is invincible? Of course not. People with dark skin can still get skin cancer, especially in areas with less melanin, like the palms of the hands or soles of the feet. They can still experience sun damage. And because skin cancer is rarer in darker-skinned populations, it's sometimes diagnosed later at more advanced stages, which makes it more dangerous. But statistically, structurally, biologically, dark skin provides profound protection against one of the most common environmental threats humans face. And this protection wasn't designed, it wasn't planned. It emerged because the individuals who had it survived slightly more often, reproduced slightly more successfully, and passed those genes forward, over and over, across hundreds of thousands of years, until dark skin became the baseline, the default, the original human phenotype. It's a masterpiece of evolutionary engineering, invisible and automatic, working every single day to keep your DNA intact. But remember, protection is only half the equation. Because while dark skin was defending against UV damage, it was also defending something even more fragile, something most people have never even heard of. And that's where we're going next. There's a vitamin most people have never heard of, and yet without it, you wouldn't be here. Your parents wouldn't have been born. Your ancestors wouldn't have survived long enough to pass on their genes. It's called folate, sometimes known as vitamin B9, and it's one of the most critical molecules in your body. And here's the thing that's going to surprise you. The sun destroys it. That's right. The same sunlight that gives you vitamin D is actively breaking down another essential nutrient in your bloodstream, and dark skin evolved in large part to protect it. Let's start with what folate actually does, because this is where the story gets intimate. Folate is involved in synthesizing DNA. Every time a cell in your body divides, it needs to copy its entire genetic code, all 3 billion base pairs, and folate is essential for building the nucleotides that make up that code. Without adequate folate, cell division slows down or produces errors. This affects rapidly dividing cells most dramatically, which means your bone marrow, where red blood cells are constantly being produced, and your gut lining, which regenerates every few days, and, perhaps most critically, developing embryos. During the first few weeks of pregnancy, often before a woman even knows she's pregnant, the embryo's neural tube is forming. This structure will become the brain and spinal cord. The neural tube starts as a flat sheet of cells that must fold and seal itself into a closed tube. This process requires massive amounts of cell division and DNA synthesis, which means it requires folate. Lots of it. If folate levels are too low during this critical window, the neural tube doesn't close properly. The result is a group of devastating birth defects, collectively called neural tube defects. Spina bifida is one. The spinal column doesn't close completely, leaving the spinal cord exposed or improperly protected. Depending on the severity, this can cause paralysis, loss of sensation, bowel and bladder problems, and lifelong disability. Anencephaly is even more severe. The brain doesn't develop properly, and babies with anencephaly are often stillborn or die shortly after birth. These aren't rare historical curiosities. Even today, in countries where folate fortification isn't standard, neural tube defects occur in about 1 in every 1,000 births. And the cause, more often than not, is folate deficiency during early pregnancy. Now, imagine you're living in equatorial Africa 10,000 years ago. You're outside all day, every day. The sun is intense, direct, unrelenting, and ultraviolet radiation, specifically UVA, penetrates into your skin and into the tiny blood vessels just beneath the surface. When UV radiation hits folate circulating in your bloodstream, it breaks it down. The molecule is photosensitive. It degrades under UV exposure. Studies have shown that just 1 hour of intense sun exposure can significantly reduce folate levels in people with light skin. For someone with dark skin, the melanin acts as a shield. It absorbs most of the UV radiation before it reaches the blood vessels. Folate remains intact. For someone with light skin in that same environment, folate is being destroyed faster than the body can replenish it through diet. And remember, folate isn't just important during pregnancy. It's needed constantly for DNA synthesis in all your cells. Low folate leads to anemia, fatigue, immune dysfunction, and poor wound healing. But the reproductive consequences are the ones that mattered most to natural selection. Think about it from an evolutionary perspective. A woman living near the equator with light skin would be at constant risk of folate deficiency. If she became pregnant, the chances of neural tube defects would be higher. Even if the child survived birth, developmental problems could reduce their chances of surviving to adulthood. Over generations, women with darker skin, women whose melanin protected their folate levels, would have healthier children. Those children would survive more often. The genes for darker skin would spread. Natural selection doesn't require massive differences in survival. Even a small advantage, repeated across thousands of generations, is enough to shift the entire population. And it's not just women. Men need folate too. Folate is critical for sperm production. Studies have shown that folate deficiency in men is associated with reduced sperm count and increased rates of chromosomal abnormalities in sperm. In a species where reproductive success is everything, where passing on your genes is the only currency that evolution recognizes, protecting folate isn't optional. It's essential. This is why dark skin persisted so strongly in equatorial populations. It wasn't just about preventing skin cancer, which often appears later in life after peak reproductive years. It was about protecting a molecule that's needed right now, constantly, especially during the most vulnerable moments of new life. Folate is fragile, sunlight is relentless, dark skin is the solution. Now let's flip the scenario. Imagine those same humans migrating north, into Europe, into Asia. Suddenly the sun is weaker. Winter days are short. UV radiation isn't pounding down all year. The threat to folate decreases dramatically. At the same time, the need for vitamin D becomes urgent. In this new environment, dark skin is overprotective. It's blocking UV radiation that's barely sufficient to produce vitamin D, and it's protecting folate that isn't really under threat. The evolutionary pressure flips. Light skin becomes advantageous because it allows more UV penetration for vitamin D synthesis without causing significant folate destruction. This is the balancing act I mentioned earlier. Folate protection versus vitamin D production. Too much melanin in a low UV environment and you risk vitamin D deficiency. Too little melanin in a high UV environment and you risk folate deficiency. Your skin color is your body's answer to that equation, calibrated over thousands of generations to match the UV intensity of the region where your ancestors lived. And here's something that might change how you think about prenatal care. Modern medicine recognized the importance of folate decades ago. That's why pregnant women are advised to take folic acid supplements, the synthetic form of folate. That's why many countries fortify foods like bread and cereal with folic acid. These public health interventions have dramatically reduced the rate of neural tube defects. But they're essentially compensating for the fact that many people now live in environments their skin wasn't designed for, or they live modern lifestyles that don't match the evolutionary context in which their skin color evolved. A fair-skinned woman living in Australia under intense sun loses folate rapidly and needs supplementation. A dark-skinned woman living in Sweden with minimal sun exposure produces vitamin D poorly and may need supplementation. Neither situation is a flaw in design. They're mismatches between biology and environment. Your skin was calibrated for a specific latitude, a specific UV intensity. When you live somewhere else, or when modern life keeps you indoors under artificial light, the system that worked perfectly for your ancestors doesn't work quite as well for you. But the fact remains. For hundreds of thousands of years, dark skin protected folate. It safeguarded pregnancies. And this invisible, molecular-level protection is just as important as the visible protection against sunburn and cancer. Folate is life, quite literally, and melanin is its bodyguard. But while dark skin was defending folate in the sun-drenched south, humans moving north faced an entirely different crisis. And that's the story we turn to next. Now let's travel north, far north. Imagine standing in what is now Scandinavia, 30,000 years ago. The sun barely crests the horizon before sliding back down. When it does appear, it's weak, pale, filtered through clouds and mist. You're wrapped in animal furs because the temperature is well below freezing. And here's the problem. Your body needs sunlight to survive. Not for warmth, though that helps. Not for mood, though that matters too. For something much more fundamental. A molecule called vitamin D that your skin can only produce when ultraviolet B radiation strikes it. And in this frozen, dim world, there's almost no UVB to be found. Vitamin D is one of those nutrients that seems simple until you dig into what it actually does, and then you realize your entire body depends on it. Let's start with the most obvious function. Vitamin D regulates calcium absorption in your gut. Without it, you can eat all the calcium you want, drink milk, chew bones, whatever, and your body won't absorb it efficiently. Calcium then gets pulled from your bones to maintain the levels your blood needs for nerve function and muscle contraction. Over time, your bones become soft, weak, prone to fractures. In children, this is called rickets. In adults, it's osteomalacia. Both are painful, debilitating, and in severe cases, deadly. But vitamin D does far more than build bones. It modulates your immune system, helping it respond to infections without overreacting into autoimmune chaos. It influences cell growth and differentiation, which means it plays a role in preventing cancer. It affects your cardiovascular system, your muscle function, even your brain. Low vitamin D levels are associated with depression, particularly seasonal affective disorder. That heavy, exhausted sadness that descends during dark winter months. Some researchers believe vitamin D affects neurotransmitter synthesis, including serotonin, the mood-regulating chemical that also helps you sleep well. So vitamin D isn't optional, you need it. And your body has an elegant way of making it. Assuming you have access to sunlight, here's how it works. When UVB radiation, the specific wavelength between 280 and 320 nanometers, hits your skin, it strikes a molecule called 7-dehydrocholesterol. This is a form of cholesterol sitting in your skin cells, waiting. The UVB photon provides enough energy to break a chemical bond, rearranging the molecule into previtamin D3. Over the next few hours, body heat converts previtamin D3 into vitamin D3, also called cholecalciferol. This then travels to your liver, where it's converted into calcidiol, and finally to your kidneys, where it becomes calcitriol, the active form your body can actually use. It's a multi-step process, and it starts with sunlight hitting skin. No sunlight, no vitamin D, well, almost. You can get small amounts from food, fatty fish like salmon and mackerel, egg yolks, liver, but for most of human history, dietary sources were inconsistent. Your skin was the primary factory, and here's where the problem begins. Melanin interferes with this process. Remember, melanin absorbs UV radiation. That's its job, but it doesn't distinguish between harmful UVA and useful UVB. It blocks both. The more melanin you have, the more UVB gets absorbed before it can convert 7-dehydrocholesterol into previtamin D3. Studies have quantified this. A person with very dark skin might need 5 to 10 times more sun exposure than a person with very light skin to produce the same amount of vitamin D. In equatorial Africa, this isn't a problem. The sun is so strong, so direct, so present year-round, that even with melanin blocking most of the UVB, enough gets through. But move that same person to Scotland or Norway or Sweden, where winter days last only a few hours and the sun barely rises above the horizon, and suddenly they're in trouble. The weak sunlight that does arrive is further blocked by melanin, and to make matters worse, cold weather means people are covered head to toe in clothing. Almost no skin is exposed. For early humans migrating into these northern latitudes, dark skin became a liability. Children would develop rickets. Bones would soften and bow under body weight. Growth would be stunted. Pain would be constant. Pregnant women would face complications. Adults would suffer fractures from minor injuries. And because vitamin D affects so many systems, immune function would decline, mood would drop, overall health would deteriorate. These aren't minor inconveniences. These are survival-level problems. Natural selection doesn't wait around. Over thousands of years, individuals with slightly lighter skin, individuals whose melanin was less dense or less concentrated, had an advantage. They could produce vitamin D more efficiently from the limited sunlight available. Their bones were stronger. Their children were healthier. They survived the brutal northern winters better and lived long enough to reproduce. The genes for lighter skin, genes that reduced melanin production or changed its distribution, spread through the population. This wasn't a sudden change. It took time. Estimates suggest that European populations began lightening somewhere between 10,000 and 30,000 years ago, though the exact timeline is still debated. But the genetic evidence is clear. Mutations in genes like SLC24A5, which affects pigmentation, became increasingly common in European populations. These mutations weren't creating something new, they were reducing something old. They were dialing down melanin production just enough to let more UVB through without removing sun protection entirely. And this happened independently in different populations. East Asians also developed lighter skin, but through different genetic pathways. The mutations aren't the same, but the outcome is similar. Convergent evolution again. Same problem, same solution, different genetic route. This tells us that the pressure to lighten skin in low UV environments was strong and consistent across multiple human populations. But here's where it gets really interesting. Not all northern populations lightened. The Inuit people, living in the Arctic, one of the lowest UV environments on Earth, retained relatively dark skin. Why? Because they had an alternative solution. Their traditional diet is rich in fatty fish and marine mammals, animals whose fat and organs contain high levels of vitamin D. Seals, whales, salmon, these foods provided the vitamin D their bodies needed without requiring them to produce it from sunlight. The evolutionary pressure to lighten their skin was reduced because they had a dietary workaround. This is a crucial point. Evolution is flexible. It finds solutions wherever they exist. If you can solve a problem through diet, you don't need to solve it through skin color. But for most populations moving into Europe and Northern Asia, fish weren't abundant or accessible year-round. They relied on terrestrial animals, grains, foraged plants. Dietary vitamin D was scarce. Skin-based production was essential. And so their skin lightened. Today, vitamin D deficiency is a global problem, but it affects people with dark skin living in northern latitudes particularly severely. A person of African or South Asian descent living in the United Kingdom or Canada is at high risk of vitamin D deficiency, especially during winter. Their skin is adapted to equatorial sun, not the dim, angled light of northern winters. Rickets, once nearly eradicated, has reappeared in these populations. Supplementation and dietary fortification help, but they're modern interventions compensating for an evolutionary mismatch. So light skin isn't inherently better. It's better for one thing, producing vitamin D efficiently in low UV environments. That's it. It's a trade-off. Less sun protection, more vitamin D production, and in places where the sun is weak and winter is long, that trade-off was worth it. Your ancestors' skin lightened because it had to. Because bones needed calcium, because children needed to grow, because survival in the north required wringing every possible photon of UVB out of the pale winter sky. But while lighter skin solved the vitamin D crisis, it created a new vulnerability, and that's where our story turns next. There's a disease that sounds almost medieval, something from a time before modern medicine, before vitamins were even understood, but it isn't ancient. It swept through the industrial cities of Europe and North America well into the 20th century, crippling children by the thousands. It was called rickets, and it became the unintentional proof that light skin wasn't just a cosmetic variation. It was a biological necessity for survival in northern climates, and the story of how rickets was finally conquered reveals just how critical the balance between sun, skin, and vitamin D really is. Let's set the scene. It's the late 1800s, the height of the Industrial Revolution. Cities like London, Manchester, Glasgow, and later New York and Chicago are booming. Factories are churning out steel, textiles, machinery. Coal smoke pours from thousands of chimneys, blackening the sky. The air is thick, heavy, filled with soot and sulfur. Sunlight, what little manages to penetrate the northern latitudes' already weak rays, is filtered and scattered by this industrial haze. The cities are dark, even at midday. And the people living in these cities are crowded into tenements, narrow buildings, packed tightly together, blocking what little light might reach the streets. Families live in single rooms with one small window, if they're lucky. Children work in factories, in mines, indoors for 12 or 14 hours a day. When they're not working, they're inside, because the streets are filthy and dangerous. No one is getting sunlight, almost no one. Then doctors started noticing something alarming. Children, particularly poor children, were developing horribly deformed bones. Their legs bowed outward or knocked inward under the weight of their own bodies. Their spines curved. Their ribs developed strange bumps, creating what was called a rachitic rosary. Their skulls softened, their growth stunted. They were in constant pain. Walking was difficult. Some couldn't walk at all. This was rickets, though at the time no one understood what caused it. The medical community was baffled. Some thought it was genetic. Others blamed poor sanitation or infectious disease. A few suspected diet, but they couldn't pinpoint what was missing. The truth was hidden in plain sight, or rather, hidden in the absence of light. These children weren't getting enough vitamin D because they weren't getting enough sunlight. Their skin, even though many of them had the pale skin adapted for northern climates, couldn't produce vitamin D without UVB radiation. And in the smoke-choked cities of industrial Europe, UVB was nearly non-existent. Without vitamin D, their bodies couldn't absorb calcium properly. Calcium is essential for bone mineralization, the process that makes bones hard and strong. In growing children, whose bones are rapidly forming and lengthening, calcium deficiency is catastrophic. The bones continue to grow, but they don't harden. They remain soft, flexible, easily deformed. When a child tries to stand or walk, their leg bones bend under the pressure. The deformities become permanent. Rickets was so common in some industrial cities that it became normalized. Bowed legs were just what poor children looked like, but it wasn't normal. It was a preventable nutritional deficiency caused by an environmental mismatch. Humans had evolved light skin to maximize vitamin D production in low-light environments, but industrialization had created an environment even more extreme than evolution had prepared for. The breakthrough came slowly, in pieces. In the early 1900s, researchers began experimenting with cod liver oil, a traditional remedy in some coastal communities. Cod liver oil is extraordinarily rich in vitamin D, though at the time, no one knew what vitamin D was. They just knew that children given cod liver oil seemed to recover from rickets. Then, in 1919, a British doctor named Edward Mellanby conducted controlled experiments with dogs, inducing rickets and then curing it with cod liver oil. He concluded that rickets was caused by a dietary deficiency of something he called an accessory food factor. Around the same time, other researchers discovered that exposing children to sunlight or even to artificial ultraviolet lamps could also cure and prevent rickets. It was confusing. How could both a food and sunlight treat the same disease? The answer came in 1922, when Elmer McCollum isolated the active compound in cod liver oil and named it vitamin D. Further research showed that skin produces the same vitamin when exposed to UV light. Finally, the puzzle was solved. Rickets was vitamin D deficiency, caused either by lack of sunlight or lack of dietary sources. This discovery transformed public health. Cod liver oil, despite its awful taste, became a standard supplement for children. Milk and other foods were fortified with vitamin D. Public health campaigns encouraged parents to take their children outside, to let them play in parks where sunlight could reach them. Anti-pollution laws began to clear the air in industrial cities. And rickets, which had affected up to 80 or 90% of children in some urban areas, began to disappear. But here's the deeper lesson. Rickets revealed that light skin wasn't just about appearance or ancestry, it was functional biology. European populations had evolved lighter skin over thousands of years, specifically to maximize vitamin D production in environments where sunlight was scarce. And even that adaptation wasn't enough when industrial pollution blocked the sun entirely. The disease demonstrated that skin color and environment are locked in a delicate balance. Push that balance too far, and bodies break down. It also showed that evolution works on timescales far longer than human culture. Industrialization happened in the span of a few generations. Evolution can't respond that quickly. The children suffering from rickets didn't have time to evolve even lighter skin or more efficient vitamin D synthesis. They needed intervention. They needed science to step in where evolution couldn't. Today, rickets is rare in developed countries, but it hasn't disappeared. It still appears in children with dark skin living in northern latitudes, particularly when they're exclusively breastfed without vitamin D supplementation, or when they have limited sun exposure due to cultural practices, clothing, or simply spending too much time indoors. The biology hasn't changed. Dark skin still produces vitamin D more slowly. Northern latitudes still provide weak, seasonal sunlight, and without supplementation or dietary sources, deficiency still leads to softened bones. The rickets epidemic was a historical accident, a collision between evolutionary biology and industrial society, but it taught us something profound. Your skin color isn't arbitrary, it's calibrated. It's a biological instrument tuned to a specific range of sunlight intensity. When you live outside that range, whether because you've migrated to a different latitude or because your environment has changed around you, your body struggles. Light skin in the north solved the vitamin D problem, but only barely. It gave European populations just enough of an edge to survive long, dark winters. But it came at a cost. Because while lighter skin allowed more UVB through for vitamin D synthesis, it also allowed more UV radiation through period. The protection that dark skin provided, the shield against DNA damage, against folate destruction, against skin cancer, all of that was reduced. Light skin is more vulnerable. And as humans continue to migrate, as light-skinned populations moved back toward the equator or spent time in intense sun, that vulnerability became a problem. And that's the paradox we need to explore next. Let's travel to the equator. Not the modern equator with sunscreen and air conditioning, but the equator as it existed for most of human history. Picture standing in what is now Kenya, or Ecuador, or Indonesia. The sun rises almost directly overhead. There are no seasons in the way northern latitudes experience them, no long winter nights or endless summer days. Just consistent, relentless, powerful sunlight, day after day, year after year. The UV index here regularly reaches 11, 12, sometimes higher. For context, a UV index above 11 is considered extreme. Dermatologists recommend avoiding the sun entirely at those levels if you have fair skin. But if you're living at the equator, avoidance isn't an option. You're outside. You're farming, hunting, gathering, building, living, and your skin needs to handle it. This is where dark skin isn't just helpful, it's essential. Remember, melanin, particularly eumelanin, absorbs and scatters ultraviolet radiation before it can penetrate deep into your skin. In equatorial environments, this protection is working constantly, from sunrise to sunset, blocking an onslaught of UV that would devastate lighter skin. We've already talked about skin cancer and folate protection, but there are other layers to this story that reveal just how perfectly dark skin is adapted to high UV life. Let's start with something you might not expect: immune function. Your skin isn't just a barrier, it's an active immune organ, filled with specialized cells that detect pathogens and coordinate defensive responses. UV radiation, particularly UVB, suppresses these immune cells. It's a well-documented phenomenon called UV-induced immunosuppression. When your skin is exposed to intense UV, certain immune cells, like Langerhans cells, become less effective. They struggle to activate T cells, the soldiers of your immune system. This suppression is actually why some people get cold sores after spending time in the sun. The herpes simplex virus, which normally lies dormant, reactivates when UV exposure weakens local immune surveillance. In equatorial environments, where UV exposure is constant and intense, this immune suppression could be a serious problem. Your skin is your first line of defense against infections, and if that defense is being weakened by sunlight every single day, you're more vulnerable to bacterial and viral infections that enter through cuts, insect bites, or mucous membranes. Dark skin minimizes this. By blocking more UV radiation, it preserves immune function. The Langerhans cells stay active, the T cells remain ready. Your skin's ability to fight off pathogens isn't compromised by the very sunlight you can't escape. This matters more than you might think. Equatorial regions are also home to a huge diversity of infectious diseases: malaria, dengue, yellow fever, various parasitic infections. These are all more common near the equator, partly because of climate and ecology, but also because pathogens thrive in warm, humid environments. Having a fully functional skin immune system, one that isn't being constantly suppressed by UV radiation, is a significant survival advantage. Dark skin doesn't just protect against sunburn, it maintains your body's ability to defend itself against invisible threats. Then there's the issue of heat regulation. You might assume dark skin would absorb more heat and make you hotter, and in pure physics terms, darker surfaces do absorb more infrared radiation. But human thermoregulation is far more complex than surface color. What matters most is your ability to sweat efficiently and dissipate heat through evaporation. And here, skin color plays a surprisingly small role compared to factors like sweat gland density, body shape, and hydration status. Studies have shown that people with dark skin and people with light skin regulate temperature similarly when other factors are controlled. What does matter is keeping your sweat glands healthy. UV radiation, especially chronic exposure, can damage sweat glands over time, reducing their density and efficiency. Dark skin protects these glands from UV damage, ensuring they continue to function properly throughout your life. In an environment where overheating can be deadly, where you're physically active under brutal sun, maintaining efficient sweating isn't optional. It's survival. There's also the question of hydration and skin integrity. UV radiation breaks down collagen and elastin, the structural proteins that keep your skin firm, flexible, and intact. Over time, this breakdown leads to wrinkles, sagging, and thinner skin that's more prone to tearing and injury. In an equatorial environment, where your skin is constantly exposed to intense UV, this degradation would happen much faster without melanin protection. Dark skin preserves collagen density longer, maintaining skin strength and resilience throughout life. This isn't vanity. Intact skin is a functional necessity. It keeps water in and pathogens out. In hot climates, where dehydration is a constant risk, your skin's ability to retain moisture is critical. Thin, damaged skin loses water more rapidly through a process called transepidermal water loss. Dark skin, by protecting against UV-induced collagen breakdown, maintains a stronger moisture barrier. You stay hydrated more easily. Your skin remains a more effective shield. And let's not forget folate again, because in equatorial regions, the threat to folate isn't theoretical. It's constant. Every hour of sun exposure is breaking down this critical vitamin in light-skinned individuals. For pregnant women, for anyone of reproductive age, maintaining adequate folate levels is non-negotiable. Dark skin ensures that even with all-day sun exposure, folate remains stable, neural tube defects remain rare, DNA synthesis continues uninterrupted. This is baseline functionality in equatorial populations, but it's only possible because of melanin. There's a reason why indigenous populations at or near the equator, whether in Africa, South Asia, Oceania, or the Americas, all independently evolved or maintained dark skin. The evolutionary pressure is overwhelming. Light skin at the equator isn't just disadvantageous. It's almost incompatible with survival without modern interventions like sunscreen, protective clothing, and dietary supplementation. You'd burn constantly. Your DNA would accumulate damage at an accelerated rate, your folate would plummet, your immune system would be suppressed, your skin would age and degrade rapidly. Dark skin isn't just an adaptation, it's the adaptation for equatorial life. It's the biological response to an environment that tests every square inch of your body's largest organ, day after day, for your entire life. And the populations that have thrived at the equator for tens of thousands of years demonstrate that when your biology matches your environment, you don't just survive, you flourish. But evolution doesn't stop at the equator. As humans spread across the globe, they encountered not just different amounts of sunlight, but different kinds of challenges entirely. And in the far north, where the sun barely rises for months at a time and cold is as much a threat as UV ever was, the equation shifted once again. Light skin became essential, but even light skin wasn't enough on its own. And that's where human ingenuity stepped in to bridge the gap that evolution alone couldn't solve. Now, let's go as far north as humans have ever permanently lived. Picture the Arctic Circle, Scandinavia, Siberia, northern Canada. Places where winter doesn't just mean cold weather, it means months of near total darkness. The sun dips below the horizon in November and doesn't fully return until February. When it does appear, it's weak, barely skimming the horizon before disappearing again. The light that does reach you is angled, filtered through more atmosphere than anywhere else on Earth, which strips away most of the ultraviolet B radiation your skin needs to make vitamin D, and to survive the brutal cold. You're wrapped in furs, in layers, covering almost every inch of your body. Your face might be exposed, maybe your hands briefly, but that's it. This is one of the most extreme environments humans have ever inhabited, and the challenge it presents is different from anywhere else. At the equator, the problem is too much UV. Here, the problem is not enough. Even with light skin, which we know evolved to maximize vitamin D production in low light conditions, the northern extremes push biology to its limits. Light skin helps, absolutely. It allows more UVB to penetrate and convert that cholesterol molecule into previtamin D3. But when there's almost no UVB to begin with, even the lightest skin in the world can't manufacture enough vitamin D from sunlight alone. So how did humans survive here? How did populations in Scandinavia, Siberia, and the Arctic avoid the rickets, the bone pain, the immune dysfunction that comes with severe vitamin D deficiency? The answer is a combination of biology, culture, and diet. Let's start with the Sami people of northern Scandinavia and the various Siberian populations who have lived above the Arctic Circle for thousands of years. Many of these groups have relatively light skin, and that makes sense given the low UV environment. But even their light skin wasn't enough on its own during the long polar nights. What saved them was their diet. Fish, reindeer, seal. These foods are extraordinarily rich in vitamin D, particularly fatty fish like salmon, mackerel, and herring, and the organs and fat of marine mammals. Vitamin D is fat-soluble, which means it accumulates in the fatty tissues of animals, especially those that live in cold environments where they need thick blubber for insulation. When you eat these foods, you're consuming pre-made vitamin D, the exact same molecule your skin would produce from sunlight. Your body doesn't care where the vitamin D comes from. It just needs it. This is why populations like the Inuit, who live in one of the lowest UV environments on Earth, retained relatively darker skin compared to Scandinavians. The Inuit traditional diet is almost entirely animal-based, heavy in fatty fish, seal, whale, and caribou. These foods provide massive amounts of vitamin D, far more than most people could ever produce through sun exposure, even in summer. The evolutionary pressure to lighten their skin was reduced because they had an alternative vitamin D source. They didn't need to maximize sun-based production because they were getting it from food. This is a perfect example of how evolution is flexible and opportunistic. If there's more than one solution to a problem, evolution doesn't force a single path. It favors whatever works. For most northern European populations who relied more on terrestrial animals, grains, and forage plants, dietary vitamin D was scarce. Their survival depended on wringing every possible bit of vitamin D from the weak northern sun, so their skin lightened dramatically. For the Inuit, whose entire culture and survival strategy revolved around marine hunting, dietary vitamin D was abundant, so their skin didn't need to lighten as much. But even beyond diet and skin color, northern populations developed cultural adaptations that helped them cope with extreme darkness. In traditional Scandinavian cultures, cod liver oil was a staple, especially during winter. It tastes terrible, but it's one of the richest natural sources of vitamin D available. Children were given it regularly, often daily during the darkest months. This wasn't based on scientific understanding of vitamins, obviously, but on generations of observation that children who consumed it stayed healthier. There's also the matter of activity and lifestyle. Northern populations spent time outdoors even in winter because survival required it. Hunting, ice fishing, tending to reindeer herds. These activities meant exposing at least some skin to whatever weak sunlight was available. Even if your face is the only exposed skin, even if the sun is barely above the horizon, those few minutes of UVB exposure matter. Your body is extraordinarily efficient at grabbing whatever vitamin D it can make when given the chance. And then there's something fascinating about latitude and seasonal variation. In summer, above the Arctic Circle, the sun doesn't set. It circles the horizon continuously for weeks or even months, depending on how far north you are. This is the midnight sun, and it provides an opportunity for intense vitamin D production during a narrow window. People with light skin living in these regions can produce large amounts of vitamin D during summer, and because vitamin D is fat-soluble, it gets stored in body fat and liver tissue. This stored vitamin D can then be drawn on during the dark winter months, acting as a biological battery that carries you through until the sun returns. This seasonal storage strategy only works if you have light skin and access to strong summer sun. Dark-skinned individuals in the same environment would produce less vitamin D during summer and have smaller reserves to draw on during winter, which is why vitamin D deficiency is such a significant problem for immigrants from equatorial regions living in northern countries today. Their skin wasn't designed for this kind of extreme seasonal variation. They need either dietary supplementation or dramatically increased sun exposure during summer, and even that might not be enough. There's also clothing to consider. In the coldest regions, survival depends on staying covered, which means UV exposure is minimal even when the sun is out. But traditional northern clothing was often made from animal skins and furs that, interestingly, retained some vitamin D from the animals they came from. Whether this contributed significantly to human vitamin D intake is debated, but it's another example of how every available resource was utilized in these marginal environments. The northern extremes teach us something important. Skin color alone isn't destiny. It's one piece of a larger puzzle that includes diet, behavior, culture, and environment. Evolution shaped light skin to maximize vitamin D production in low UV environments, but humans also shaped their cultures to survive in places where even biological adaptation wasn't quite enough. We hunted the right animals. We ate the right parts. We stored vitamin D in our bodies during summer to survive winter. We passed down knowledge about cod liver oil and fatty fish. And this flexibility, this ability to adapt not just biologically but culturally, is part of what makes humans so successful as a species. We're not locked into one environment. We can survive almost anywhere, not because our bodies are perfect for every condition, but because we're smart enough to bridge the gaps. Still, there are limits. And as we're about to see, Even the most ingenious cultural adaptations can't fully compensate when biology and environment are badly mismatched. There's something melanin does that most people never learn about. Something that goes beyond blocking UV radiation or regulating vitamin D production. Melanin has antimicrobial properties. It's not just a passive shield. It's an active participant in your immune defense. And this hidden function might have played a significant role in human survival, particularly in the disease-rich environments where dark skin evolved. Let's start with what we know. Melanin, especially eumelanin, has been shown in laboratory studies to bind to and neutralize certain bacteria, viruses, and fungi. It can sequester toxic metals and free radicals, preventing them from damaging cells. It has antioxidant properties, meaning it can absorb dangerous reactive oxygen species that would otherwise cause inflammation and cellular damage. In essence, melanin isn't just sitting there absorbing light. It's chemically active, interacting with molecules in ways that protect your body from a variety of threats. Now, this research is still emerging, and we don't yet have a complete picture of how significant melanin's antimicrobial effects are in living human skin, but what we do know is intriguing. Melanin is found not just in your skin, but also in your inner ear, your brain, your eyes, and even scattered throughout other organs. This wide distribution suggests it serves multiple functions beyond pigmentation, and in the skin specifically, where melanin is most concentrated, its presence in the outer layers creates a chemical environment that may be hostile to certain pathogens. Think about what skin does. It's your barrier between the internal, sterile world of your body and the external, microbe-filled environment. Your skin is constantly exposed to bacteria, fungi, viruses, environmental toxins, all trying to get in. Most of the time, your skin stops them. The outer layer, the stratum corneum, is made of dead, keratinized cells that form a tough, relatively impermeable barrier. But it's not just a physical wall, it's also a chemical one. Your skin secretes oils, maintains a slightly acidic pH, and harbors beneficial bacteria that outcompete harmful ones. Melanin may be another part of this chemical defense system. Consider where dark skin evolved: equatorial Africa. Hot, humid, teeming with life. This includes an incredible diversity of pathogens: malaria, yellow fever, dengue, sleeping sickness, river blindness, countless bacterial and parasitic infections. Many of these diseases enter through the skin, either through insect bites, cuts, or even intact skin in some cases. Having an extra layer of chemical defense, even a modest one, could make a difference over evolutionary time. There's also the question of UV-induced immune suppression, which we touched on earlier but is worth revisiting here. When UV radiation penetrates your skin, it doesn't just damage DNA, it also suppresses local immune function. Langerhans cells, which are specialized immune cells in your epidermis, become less effective at capturing and presenting antigens to T cells. This means your skin becomes less capable of mounting an immune response to infections. In someone with light skin exposed to intense equatorial sun, this immune suppression is significant and constant. In someone with dark skin, melanin blocks much of the UV before it can suppress immune function, keeping the Langerhans cells active and responsive. So dark skin doesn't just resist infections because of melanin's direct antimicrobial properties, though that may play a role. It also resists infections by preserving the immune cells already present in the skin, preventing UV radiation from disabling them. This dual-layer protection, chemical and immunological, would have been incredibly valuable in environments where skin infections could easily become systemic and deadly without antibiotics or modern medicine. There's another angle to consider: inflammation. UV radiation triggers inflammatory responses in skin. This is part of why sunburn hurts and why your skin feels hot and swollen afterward. Chronic, low-level inflammation from repeated UV exposure contributes to aging, yes, but it also taxes your immune system, forcing it to constantly repair damage and manage inflammatory signals. Over a lifetime, this chronic inflammation can lead to immune exhaustion, where your body becomes less effective at fighting new threats because it's perpetually dealing with UV-induced damage. Dark skin reduces this inflammatory burden. By blocking UV, it prevents the initial damage that triggers inflammation. Your immune system isn't constantly in repair mode. It can stay vigilant, ready to respond to actual infections rather than being distracted by sun damage. This is speculative, but it's grounded in what we understand about inflammation and immune capacity. Your immune system has finite resources. Anything that reduces unnecessary activation preserves those resources for real threats. Now, let's talk about a specific example where melanin's protective properties might have evolutionary significance. Leprosy. This is a bacterial infection caused by Mycobacterium leprae, and it's been afflicting humans for thousands of years. Leprosy damages skin and nerves, and historically, it was devastating in many populations. Interestingly, there's evidence that people with darker skin have somewhat lower rates of leprosy, though the data is complex and influenced by many factors, including geography, genetics unrelated to skin color, and access to treatment. But some researchers have proposed that melanin's antimicrobial properties might offer modest protection against Mycobacterium leprae. The bacteria enters through skin, often through small cuts or abrasions. If melanin in the surrounding tissue can bind to or neutralize some of the bacteria, it might reduce the initial bacterial load, giving the immune system a better chance to clear the infection before it establishes itself. This is still being studied, and I want to be clear that skin color doesn't make you immune to leprosy or any other disease, but it might shift the odds slightly in your favor. There's also fascinating research on melanin and fungal infections. Fungi, like Cryptococcus neoformans, actually produce their own melanin, which helps them evade the immune system and resist antifungal treatments. This suggests that melanin, as a molecule, has inherent protective properties that even pathogens have evolved to exploit. If fungi are using melanin to defend themselves, it makes sense that human melanin might also contribute to defense, creating a more hostile environment for fungi trying to colonize skin. What's important to understand is that skin color and immune function are intertwined in ways we're only beginning to map. Dark skin isn't just about surviving the sun. It's about surviving everything the sun-drenched environments near the equator throw at you. UV radiation, intense heat, high pathogen diversity, constant exposure. Melanin handles all of it. Not perfectly, but effectively enough that humans with dark skin thrived in those environments for hundreds of thousands of years. And this is part of why reducing skin color to aesthetics or social categories misses the point entirely. Your skin color is functional biology. It's a suite of adaptations working together: UV protection, folate preservation, immune support, possibly even direct antimicrobial defense, all calibrated to the environment where your ancestors lived. It's not better or worse than any other skin color. It's adapted, and adaptation is always context dependent. What works brilliantly in one environment might struggle in another, which brings us to the modern world, where almost no one lives in the environment their skin was designed for. Here's something that might surprise you. Vitamin D deficiency is now a global epidemic, affecting people of every skin color, in every country, across every continent. The very nutrient that drove the evolution of different skin tones, the molecule that determined whether your ancestors' skin lightened or stayed dark, is now inadequate in billions of people worldwide. And the reason has almost nothing to do with skin color itself. It has everything to do with how we live now versus how we evolved to live. Let's start with the numbers, because they're staggering. Estimates suggest that roughly 1 billion people worldwide have vitamin D deficiency, and another billion have insufficient levels, meaning they're not clinically deficient but still below optimal. That's nearly a third of the human population. And this isn't just happening in one region or one demographic. It's everywhere. Northern countries, equatorial countries, wealthy nations, developing nations, people with dark skin and people with light skin. The modern world has created conditions where almost everyone is at risk. So what changed? Why are humans suddenly unable to maintain adequate vitamin D levels when our ancestors managed it for hundreds of thousands of years? The answer is simple, and it's the same across cultures. We don't go outside anymore, not like we used to. For most of human history, people spent the majority of their waking hours outdoors. Hunting, gathering, farming, herding, traveling. Even in cities, before the 20th century, much of daily life happened on streets, in markets, in open spaces. Sunlight was unavoidable. Your skin, regardless of its color, was exposed to UV radiation regularly. Now think about your own life. How much time do you spend outside? Really outside, with significant skin exposed, during the hours when UVB radiation is strong enough to produce vitamin D? For most people, the answer is almost none. You wake up indoors, you commute in a car or train, you work in an office or stay home, you exercise in a gym, you socialize indoors, you sleep indoors. On weekends, maybe you go outside, but often you're in the shade, or it's early morning or late evening when the sun is too low for effective vitamin D production. Even people who think they get plenty of sun often don't get enough UVB exposure to maintain healthy levels. And this indoor lifestyle affects everyone, but it affects people with dark skin more severely. Remember, dark skin requires significantly more sun exposure to produce the same amount of vitamin D as light skin. If a fair-skinned person needs 10 minutes of midday sun to produce adequate vitamin D, a dark-skinned person might need 30 minutes to an hour. In modern life, where even 10 minutes of direct sun exposure is rare for many people, dark-skinned individuals are at dramatically higher risk of deficiency. The data confirms this. In countries like the United Kingdom, Canada, and Sweden, vitamin D deficiency rates among people of African, South Asian, and Middle Eastern descent are alarmingly high, sometimes affecting 70 to 90% of these populations, especially during winter. These are people whose ancestors evolved dark skin for equatorial environments, now living in northern latitudes with weak, seasonal sun, working indoors, and often covering their skin with clothing for warmth or cultural reasons. The mismatch is profound. But here's what's surprising. Light-skinned people aren't doing much better. Vitamin D deficiency is also rising among European and European-descended populations, even in places like Australia and Southern California where sunlight is abundant. Why? Same reason. Indoor lifestyles. And when light-skinned people do go outside, they're often wearing sunscreen, which blocks the very UVB radiation their skin needs to produce vitamin D. Sunscreen with an SPF of 30 blocks about 97% of UVB. SPF 50 blocks, 98%. Dermatologists recommend sunscreen to prevent skin cancer, which is a valid concern, especially for fair skin. But the unintended consequence is widespread vitamin D insufficiency is less than -0. Then there's clothing. In many cultures, modesty norms mean covering most of the body year-round. Long sleeves, long pants, head coverings. This drastically reduces the skin surface area available for vitamin D production. Even in sunny climates, if only your hands and face are exposed and you're using sunscreen on those areas, you're producing almost no vitamin D from sunlight. Again, this affects people of all skin colors, but the impact is most severe for those with dark skin who need more exposure to begin with. There's also latitude and season. During winter months in northern latitudes, roughly above 37 degrees, the sun's angle is so low that UVB radiation is almost entirely filtered out by the atmosphere, even on clear days. This means that from roughly November through February, people living in places like Boston, London, Berlin, or Toronto produce virtually no vitamin D from sunlight, regardless of skin color. Your skin could be outside all day and it wouldn't matter. The wavelength you need simply isn't reaching you. The result is predictable. Vitamin D levels drop during winter, especially in people who aren't supplementing. Fatigue increases. Mood deteriorates. This is part of what drives seasonal affective disorder, that heavy depression that descends in winter and lifts in spring. Low vitamin D affects serotonin synthesis, the neurotransmitter that regulates mood and sleep. When your vitamin D drops, your serotonin can drop too, leaving you feeling sad, sluggish, and struggling to get restful sleep. And sleep is where this all connects more directly than you might expect. Vitamin D receptors are found throughout your brain, including areas that regulate your circadian rhythm, your body's internal clock that controls sleep-wake cycles. Emerging research suggests that vitamin D deficiency is associated with poor sleep quality, difficulty falling asleep, frequent waking, and shorter total sleep duration. Some studies have found that people with vitamin D deficiency are more likely to have obstructive sleep apnea, restless leg syndrome, and other sleep disorders. The mechanism isn't fully understood, but vitamin D appears to influence melatonin production, the hormone that signals your body it's time to sleep. It also affects inflammation and pain sensitivity, both of which can disrupt sleep. If you're deficient in vitamin D, you might be experiencing poor sleep without realizing the connection. You might think it's stress, or screens, or caffeine, and those factors certainly matter. But underneath it all, your body might simply be lacking a nutrient it evolved to produce naturally from sunlight. So, what's the solution? For most people, it's supplementation. Vitamin D. 3 supplements, the same form your skin produces, are widely available, inexpensive, and effective. The recommended daily intake varies depending on who you ask, but many experts suggest 1,000 to 2,000 international units per day for most adults, sometimes more for people with dark skin or those living in northern latitudes. Some people need even higher doses if they're severely deficient, but that should be determined through blood testing and medical guidance. Dietary sources help too, though they're limited. Fatty fish like salmon, mackerel, and sardines, egg yolks, fortified milk and cereals, cod liver oil, if you can stand it. But realistically, it's difficult to get enough vitamin D from food alone unless you're eating fatty fish almost daily, which most people aren't. Supplementation is the most practical approach for modern life. And if you can get outside, do it. Even 15 to 30 minutes of midday sun exposure several times a week, with arms and legs exposed and no sunscreen, can significantly boost your vitamin D levels if you have light to medium skin. For darker skin, you'll need longer exposure, closer to an hour. Yes, this contradicts the always wear sunscreen advice, and you'll need to balance cancer risk with deficiency risk based on your individual skin tone and health history. But the point is, sunlight isn't your enemy. It's what your skin was designed to use. The vitamin D paradox of the modern world is this. We evolved skin colors perfectly calibrated to specific environments, and then we moved to different environments, and then we moved indoors entirely. Evolution can't keep up with cultural change that happens in just a few generations. Your skin is still trying to function the way it did 10,000 years ago, but the world you live in is nothing like the world it evolved for. And so we all, regardless of skin color, find ourselves deficient in the very nutrient that once determined what we looked like. We've spent a lot of time talking about vitamin D deficiency and how it affects people with dark skin living in northern climates. But let's flip the equation. What happens when people with light skin live in places with intense, year-round sun? What happens when the evolutionary protection that served them well in northern Europe suddenly becomes a vulnerability under equatorial or subtropical skies? The answer is folate deficiency, skin cancer, and a stark reminder that every adaptation has its limits. Light skin evolved to maximize vitamin D production in low UV environments. It does this by reducing melanin, which means it also reduces protection against ultraviolet radiation. This trade-off worked beautifully in places like Scandinavia or northern Britain, where the sun is weak and the risk of UV damage is minimal. But take that same light skin and place it in Australia, South Africa, or the southern United States, and suddenly you're dealing with UV exposure levels your skin was never designed to handle. Let's start with folate, because this is where the biological mismatch becomes most clear. Remember, UV radiation destroys folate circulating in your bloodstream. Dark skin protects folate by blocking UV before it penetrates deep enough to reach blood vessels. Light skin doesn't provide this protection. It allows UV to pass through more easily, which is great for vitamin D synthesis, but terrible for folate preservation. In high UV environments, people with light skin lose folate rapidly. Studies have demonstrated this clearly. Fair-skinned individuals exposed to intense sunlight show significant drops in serum folate levels within just an hour or two. Over time, chronic sun exposure without adequate folate intake through diet or supplements can lead to deficiency. And we've already discussed what folate deficiency means: impaired DNA synthesis, anemia, fatigue, and most critically for evolutionary fitness, increased risk of neural tube defects in developing fetuses. This is why prenatal vitamins contain folic acid, the synthetic form of folate. It's standard medical advice for anyone who might become pregnant to take folic acid supplements, specifically to prevent neural tube defects like spina, bifida, and anencephaly. But what's interesting is that this recommendation became universal largely because of research conducted in populations living in sunny climates, where folate destruction from UV exposure is a significant issue. Fair-skinned women living in places like Arizona, Australia, or South Africa are at particularly high risk if they're not supplementing. And it's not just about pregnancy. Folate is needed constantly for cell division throughout your body. Low folate levels contribute to cardiovascular disease, cognitive decline, and poor immune function. Fair-skinned people living in high UV environments face a chronic nutritional challenge that dark-skinned people in the same environment simply don't experience to the same degree. The sun is literally breaking down an essential vitamin faster than diet alone can replace it. Then there's skin cancer, and this is where the mismatch becomes most visible and most deadly. Skin cancer rates among fair-skinned populations in sunny countries are astronomical. Australia has the highest rate of skin cancer in the world, and it's not even close. About 2 out of 3 Australians will be diagnosed with skin cancer by the age of 70. 2 out of 3. That's not a small risk, that's a near certainty. Why? Because most Australians are descended from British and Irish immigrants who arrived in the 18th and 19th centuries. They brought with them the pale, sun-sensitive skin that had evolved over thousands of years in cloudy northern Europe. And then they settled in one of the sunniest, highest UV countries on Earth. The UV index in Australia regularly reaches 11, 12, 13 during summer. For fair skin, this is catastrophic. The melanin protection that would shield their DNA simply isn't there. Melanoma, the deadliest form of skin cancer, is 4 times more common in Australia than in the UK. Basal cell and squamous cell carcinomas, the more common but less aggressive types, are diagnosed so frequently that many dermatologists in Australia perform multiple skin cancer removals every single day. This isn't a minor health issue. It's a public health crisis driven by evolutionary mismatch, people with the wrong skin color for the environment they live in. And it's not just Australia. South Africa has similar issues among its white population, descended largely from Dutch, German, and British settlers. The American South, particularly states like Texas, Arizona, and Florida, sees high skin cancer rates among fair-skinned residents. Even Southern California, despite its reputation for beach culture and sun worship, has significant skin cancer incidence. The pattern is consistent. Take light skin, expose it to intense, chronic UV radiation, and cancer rates skyrocket. The cumulative UV exposure is what matters most. Every sunburn, every afternoon at the beach, every hour spent gardening without sunscreen, it all adds up. UV radiation causes mutations in skin cell DNA. Most of these mutations get repaired or cause the cell to self-destruct, but occasionally a mutation slips through in a gene that controls cell division. The cell starts multiplying uncontrollably. That's cancer. And the more UV exposure you have over your lifetime, the more chances there are for one of those critical mutations to occur. Dark skin dramatically reduces this risk because melanin intercepts the UV photons before they can strike DNA. It's not perfect protection, but it's substantial. Light skin, especially very fair skin with red or blonde hair, offers minimal protection. The melanin just isn't there in sufficient quantity. Every time UV radiation hits that skin, it's a roll of the dice. And if you're rolling the dice every day for 70 years, eventually, statistically, you're going to come up unlucky. There's also the issue of immune suppression, which we've touched on before. UV radiation suppresses the immune cells in your skin that are responsible for detecting and destroying cancerous cells before they can grow into tumors. This is called immunosurveillance, and it's one of your body's primary defenses against cancer. Fair skin allows more UV through, which means more immune suppression, which means less effective cancer surveillance. It's a double hit. More DNA damage plus less immune defense equals higher cancer rates. Modern public health campaigns try to address this. Slip, slop, slap in Australia. meaning slip on a shirt, slop on sunscreen, slap on a hat. It's drilled into children from an early age. Sun protection is a cultural norm, and it's helped. Skin cancer rates in younger generations are starting to stabilize or even decline slightly in some regions. But the rates are still extraordinarily high because the fundamental biological mismatch remains. Fair skin in high UV environments is inherently vulnerable, and no amount of sunscreen can completely eliminate the risk. There's also aging to consider. UV radiation accelerates skin aging through a process called photoaging. It breaks down collagen and elastin, the proteins that keep skin firm and smooth. It causes wrinkles, sunspots, rough texture, and sagging. People with fair skin, living in sunny climates, often look significantly older than their chronological age because their skin has been under UV assault for decades. This isn't just cosmetic. Photoaging is a visible marker of accumulated DNA damage. The same processes causing wrinkles are also increasing cancer risk. So what's the solution? Ideally, people would live in environments their skin is adapted for, but that's not realistic in a globalized, mobile world. The practical answer is aggressive sun protection. Sunscreen, protective clothing, wide-brimmed hats, seeking shade during peak UV hours, and, crucially, folate supplementation for anyone at risk, especially women of childbearing age. But even with these interventions, fair-skinned people in high UV environments are playing defense against biology. They're compensating for an evolutionary mismatch that wouldn't exist if they lived where their ancestors came from. And this is the uncomfortable truth about skin color. It's not arbitrary, it's not cosmetic. It matters. It matters medically, nutritionally, and practically. Your skin color is calibrated to a specific environment, and when you live outside that environment, there are consequences. Sometimes those consequences can be managed, sometimes they can't. And that brings us to something even more complex, the reality that skin color isn't just about latitude and sunlight. It's about the beautiful, messy, unpredictable spectrum of human variation. If you've been listening carefully, you might have noticed that I've been talking about skin color as if it's simple. Dark skin near the equator, light skin in the north, a clean gradient following latitude, but human biology is never that tidy. The reality is far more complex, far more beautiful, and far more interesting than any simple model can capture. Skin color isn't a binary. It's not even a simple spectrum. It's a multidimensional tapestry woven from dozens of genes, environmental factors, and evolutionary histories that don't always follow predictable patterns. Let's start with the most obvious complexity. Siblings with the same parents can have noticeably different skin tones. You've probably seen this in your own family or among friends. One child comes out darker, another lighter, even though they share the same genetic background. This happens because skin color is polygenic, meaning it's controlled by multiple genes, not just one. Current research suggests that at least 10 to 15 different genes contribute significantly to skin pigmentation, and probably many more have minor effects. Each parent contributes one copy of each gene to their child, but which specific copy gets passed down is random. Think of it like shuffling 2 decks of cards and dealing a hand. 2 siblings from the same parents are drawing from the same decks, but they're not getting the same cards. One might inherit more of the variants that code for higher melanin production, while another inherits more of the variants that reduce it. The result is a range of skin tones within a single family, all equally natural, all equally valid expressions of that family's genetic diversity. And this diversity isn't just random noise, it's functional. Having variation in skin tone within a population provides evolutionary flexibility. If the environment changes, if a population migrates to a different latitude, or if climate shifts alter UV exposure, having a range of skin tones means some individuals will be better adapted to the new conditions. Those individuals are more likely to survive and reproduce, and over time, the population average shifts. Genetic diversity is insurance against environmental uncertainty. Now let's talk about populations that don't fit the latitude rule at all. The Inuit are the most famous example. They live in one of the lowest UV environments on Earth, the Arctic, where you'd expect extremely light skin based on the vitamin D logic we've been discussing. But Inuit people have relatively medium to tan skin, much darker than Scandinavians who live at similar latitudes. Why? Because their traditional diet is loaded with vitamin D from marine mammals and fish. The evolutionary pressure to lighten skin was reduced or eliminated because they solved the vitamin D problem through food instead of sun exposure. Then there are the people of Tibet and the high Andes, living at extreme altitudes where UV radiation is actually more intense than at sea level, but the climate is cold and harsh. You might expect very dark skin to protect against the elevated UV, but many Tibetan and Andean populations have medium skin tones, lighter than equatorial populations, but darker than European populations. The reasons are still being studied, but it likely involves a complex interplay of UV exposure, dietary factors, cold adaptation, and genetic drift. Evolution doesn't always optimize for just one variable. It balances multiple pressures simultaneously. There's also the fascinating case of indigenous Australians. Aboriginal Australians have some of the darkest skin tones in the world, comparable to or even darker than many African populations. This makes perfect sense given that Australia sits at relatively low latitudes with intense UV exposure. But here's the twist. Genetic studies show that Aboriginal Australians have been isolated from African populations for at least 50,000 years. Their dark skin evolved or was maintained independently, in parallel with African populations, because they faced similar UV pressures. It's another example of convergent evolution, where similar environmental challenges produce similar biological solutions through entirely separate genetic pathways. And what about populations that have mixed ancestry, which increasingly describes most of humanity? When people from different ancestral backgrounds have children, the offspring inherit a blend of skin tone genes from both parents. This creates intermediate shades that might not match either parent exactly. A child with one dark-skinned parent and one light-skinned parent might have skin tone right in the middle, or they might lean more toward one parent, or they might land somewhere entirely unique depending on which specific gene variants they inherited. This blending has been happening throughout human history, but it's accelerated dramatically in recent centuries, with increased global migration and intermarriage. The result is that skin tone categories that might have seemed distinct 1,000 years ago are now blurred, overlapping, and continuous. There are people with skin tones that don't fit neatly into any traditional category because their ancestry draws from multiple continents. And this is normal. This is human. We've always been a mixing, migrating, interbreeding species. There's also the role of non-UV factors in shaping skin color. Carotenoids, the pigments found in orange and yellow vegetables like carrots and sweet potatoes, can accumulate in your skin and give it a slightly golden or peachy tint. This isn't melanin, but it affects how your skin looks. Some researchers have even suggested that in certain populations, dietary preferences might have influenced sexual selection for skin tone, though this is highly speculative and difficult to prove. Hormones also play a role. Pregnancy often darkens skin temporarily, especially in areas like the face, nipples, and a line down the abdomen called the linea nigra. This is due to hormonal changes that increase melanin production. After pregnancy, skin usually lightens again, but not always to exactly the same shade. Age affects skin tone too. Many people notice their skin lightens slightly as they get older, or they develop uneven pigmentation with age spots and areas of lighter skin appearing. Melanocyte function changes over time, and melanin production becomes less uniform. Then there are genetic conditions that dramatically affect pigmentation. Albinism is the most well-known, a group of genetic disorders where melanin production is severely reduced or absent entirely. People with albinism have very pale skin, white or light-colored hair, and light-colored eyes, regardless of their ancestral background. A person of African descent with albinism might have skin as pale as someone of Scandinavian descent, even though their other genetic traits and ancestry are entirely different. This shows that skin color is controlled by a relatively small set of genes that can be altered independently of everything else that makes you who you are. On the flip side, there are conditions like melasma, where patches of skin become much darker due to hormonal triggers, sun exposure, or both. Vitiligo causes patches of skin to lose pigmentation entirely, creating stark contrasts on the same body. These conditions remind us that skin color isn't fixed. It's dynamic, responsive, and variable, even within a single individual over time. And let's not forget freckles, moles, and birthmarks. Freckles are small, concentrated areas of melanin that darken with sun exposure, most common in fair-skinned people with variants in the MC1R gene, the same gene associated with red hair. Moles are clusters of melanocytes that produce localized dark spots. Birthmarks can be hyperpigmented or hypopigmented, present from birth, caused by various developmental factors. Your skin is not one uniform color. It's a landscape of variation, a map of your genetic inheritance, your sun exposure history, your age, and your individual biology. So when we talk about skin color, we're really talking about averages, tendencies, and general patterns. We're simplifying an extraordinarily complex trait for the sake of understanding evolutionary principles. But the truth is, every person's skin is unique. No two people have exactly the same shade, the same undertones, the same distribution of pigment. Skin color is a spectrum, yes, but it's a spectrum with infinite gradations, influenced by genetics, environment, age, health, and chance. And that's not a problem. That's the point. Variation is the raw material of evolution. It's what allows populations to adapt. It's what makes us resilient as a species. And it's what makes humanity, in all its shades, so beautifully diverse. There's a question that comes up surprisingly often when people start thinking about skin color and evolution. Does skin color affect how hot or cold you get? It seems logical, right? Darker surfaces absorb more heat. Lighter surfaces reflect it. We see this with cars, with clothing, with roofs. So surely dark skin must make you hotter in the sun, and light skin must help you stay cooler. Except biology, as usual, is far more complicated than simple physics would suggest. And the answer involves sweat glands, blood flow, body shape, and a thermoregulation system so sophisticated that skin color becomes almost irrelevant to the bigger picture. Let's start with what we know from physics. Yes, darker surfaces absorb more radiation across the spectrum, including infrared, which we perceive as heat. A black car sitting in the sun will have a hotter exterior than a white car under the same conditions. But human skin isn't a car. It's a living, dynamic organ with active cooling systems. And when you factor in evaporative cooling through sweat, convective cooling from air movement, and radiant heat loss from blood vessels near the skin surface, the simple absorption story breaks down. Studies that have actually measured skin surface temperature in people with different skin tones under controlled conditions show surprisingly small differences. In some studies, dark skin does reach slightly higher surface temperatures when exposed to direct sun, maybe 1 or 2 degrees Celsius warmer than light skin. But this surface temperature difference doesn't translate to higher core body temperature, which is what actually matters for health and performance. Your core temperature, the temperature of your internal organs, stays remarkably stable regardless of skin color because your thermoregulation system is incredibly effective. Here's why. When you're hot, your body has several ways to cool down. The most important is sweating. Sweat glands release water onto your skin surface, and when that water evaporates, it absorbs heat energy from your skin, cooling you down. This evaporative cooling is so effective that it can remove enormous amounts of heat, far more than the small difference in heat absorption between dark and light skin. As long as you're sweating efficiently and the sweat can evaporate, your skin color becomes a minor variable. And humans are champion sweaters. We have more sweat glands per square inch than almost any other mammal, between 2 and 4 million sweat glands covering our entire body. We evolved this system specifically to cool ourselves during the long-distance running and persistence hunting that characterized early human survival strategies. We can run for hours in heat that would kill most other animals because we can dump heat through sweat faster than we generate it through exercise. This system works regardless of skin color. Now, there is one aspect of skin color that might matter for thermoregulation, but it's not about heat absorption. It's about UV protection of the sweat glands themselves. UV radiation, especially chronic intense exposure, can damage sweat glands over time, reducing their density and efficiency. Dark skin protects sweat glands from this UV damage, ensuring they continue to function effectively throughout life. In equatorial environments where both heat and UV are extreme, maintaining healthy sweat glands is critical. Dark skin helps with that, not by reflecting heat, but by protecting the cooling system from sun damage. There's also blood flow to consider. When you're hot, blood vessels near your skin surface dilate, bringing warm blood from your core closer to the surface where heat can radiate away. When you're cold, those vessels constrict, keeping warm blood deeper inside. This vasodilation and vasoconstriction is automatic, controlled by your hypothalamus, and it's incredibly effective at regulating core temperature. Again, this system works the same way regardless of skin color. Some researchers have investigated whether there are differences in sweat gland density or function across populations with different skin tones, and the results are mixed. Some studies suggest minor differences, possibly related to adaptation to different climates, but these differences are small and inconsistent. What matters far more than skin color is acclimatization, how adapted your body is to the specific heat conditions you're currently experiencing. Someone who's lived in a hot climate for months will thermoregulate more efficiently than someone freshly arrived, regardless of their skin tone. What about cold? Does lighter skin help you stay warmer in freezing environments? Again, the answer is no, not really. Skin color has almost nothing to do with cold tolerance. More fat means better insulation. Body shape also matters. Populations adapted to cold climates tend to have stockier builds with shorter limbs, which reduces surface area relative to body volume, minimizing heat loss. This is called Bergmann's rule and Allen's rule, and you can see it across many mammal species, not just humans. But skin color? It's irrelevant to staying warm. Northern populations, like Scandinavians and Siberians, evolved light skin for vitamin D production, not for thermal regulation. Their ability to survive brutal cold came from clothing, shelter, fire, body fat, and metabolic adaptations, not from having pale skin. Similarly, populations in hot climates stayed cool through behavioral adaptations, seeking shade during peak heat, scheduling activity for cooler parts of the day, wearing loose, breathable clothing, and yes, through their highly efficient sweating systems, but not because their dark skin made them inherently cooler. There is one interesting twist related to athletic performance. Some studies have looked at whether skin color affects performance in extreme heat or extreme cold conditions. The results are inconclusive. Elite athletes from all ethnic backgrounds and skin tones compete successfully in hot environments, from marathon runners in desert climates to soccer players in tropical humidity. Similarly, cold weather sports see successful athletes of all skin colors. Physiological factors like cardiovascular fitness, acclimatization, hydration status, and body composition matter far more than melanin. That said, there's ongoing research into whether melanin itself might have some thermal properties beyond simple radiation absorption. Some studies suggest melanin might help stabilize proteins under heat stress or protect against oxidative damage that increases in hot conditions. But these effects, if real, are subtle and not well understood. They're not the primary drivers of thermoregulation. What's clear is that humans are remarkably adaptable to temperature extremes, and skin color is a minor player in that adaptability. We've survived in every climate on Earth, from the Sahara to the Arctic, not because of skin color differences, but because of our ability to create clothing, build shelter, control fire, and modify our behavior. Our biology helps, certainly, our sweat glands, our vascular system, our metabolic flexibility, but these systems are shared across all human populations. Skin color evolved primarily for UV regulation, and it does that job exceptionally well. Temperature regulation, that's handled by other systems entirely. So if someone tells you dark skin makes you hotter or light skin makes you colder, you can gently correct them. Skin color is about managing UV radiation, protecting folate, producing vitamin D, and maintaining immune function. It's not about being a better radiator or insulator. Your thermoregulation is handled by sweat, blood flow, behavior, and body composition. Systems that work beautifully regardless of how much melanin you're carrying. And this distinction matters because it reminds us, again, that skin color is functional but specific. It solves particular problems related to sunlight. It doesn't define your overall biology. And as we move forward into the future, as humans continue to migrate, mix, and adapt, our skin color will keep evolving in ways we can barely predict. Evolution is often talked about as if it's something that happened in the past. Our ancestors evolved dark skin in Africa. Then some populations evolved lighter skin as they migrated north. Story over. But here's the thing that most people don't realize. Evolution never stops. It's happening right now, in you, in your children, in populations around the world. The forces that shaped skin color over the last 100,000 years are still operating, even if modern life has complicated the equation. So what does the future hold? Will skin color continue to change? And if so, how? Let's start with the basics of how evolution works. Natural selection requires three things. Variation in a trait, meaning people have different versions of that trait. heritability, meaning the trait is passed from parents to children, and differential reproductive success, meaning some versions of the trait lead to more surviving offspring than others. Skin color has all three. There's enormous variation across and within populations. It's clearly heritable, controlled by multiple genes, and historically, skin color has affected survival and reproduction. Darker skin protecting against UV damage and folate loss in high UV environments. Lighter skin enabling vitamin D production in low UV environments. So the machinery for continued evolution of skin color is still in place. But here's where it gets complicated. Modern life has dramatically weakened the selective pressures that drove skin color evolution in the first place. Think about it. We live indoors. We wear clothing, we use sunscreen, we take vitamin D supplements, we fortify foods with folate, we have antibiotics for infections, treatments for skin cancer, and prenatal care that catches neural tube defects early. All of these interventions reduce the survival and reproductive consequences of having the wrong skin color for your environment. A fair-skinned person living in Australia can avoid skin cancer by using sun protection. A dark-skinned person living in Sweden can avoid vitamin D deficiency by taking supplements. In evolutionary terms, this means the selective pressure has been reduced or eliminated. If skin color no longer significantly affects your chances of surviving to reproduce, then natural selection stops pushing populations toward darker or lighter skin. Evolution doesn't stop entirely, but it slows down dramatically, and it might even drift in random directions without a strong selective force guiding it. But there's another force at play, one that might be even more powerful in shaping the future of skin color: migration and interbreeding. Humans are more mobile now than at any point in history. People from different continents meet, fall in love, have children. Those children inherit a blend of genes from both parents, including genes for skin pigmentation. Over time, over many generations, this mixing creates populations with intermediate skin tones, smoothing out the extremes that evolved when populations were isolated. This is already happening. In countries like Brazil, where African, European, and indigenous American populations have been mixing for centuries. Skin tone distribution is incredibly diverse, with every shade represented and no clear categories. In the United States, which has historically tried to maintain racial boundaries through law and custom, intermarriage rates are rising rapidly. About 17% of new marriages are between people of different racial or ethnic backgrounds, and this percentage is higher among younger generations. Each of these unions produces children with blended ancestry and often intermediate skin tones. Globally, as travel becomes easier and cultural barriers to intermarriage continue to erode, this trend will likely accelerate. Some geneticists have speculated that in several thousand years, if current trends continue, humanity might trend toward a more homogeneous, medium brown skin tone, simply because the extremes will become rarer as populations continue to mix. But this is speculation. It assumes continued global mixing, which is not guaranteed. It also assumes no new selective pressures emerge, which we can't predict. And this brings up an interesting question. Could new selective pressures emerge that favor certain skin tones? Possibly, if climate change significantly alters UV exposure patterns that could create new pressures. For instance, if ozone depletion worsens, UV radiation increases globally, which might favor darker skin even at higher latitudes. Conversely, if humans spend even more time indoors than we already do, becoming almost entirely disconnected from natural sunlight, vitamin D deficiency could become even more widespread. potentially creating a weak selective pressure for lighter skin or more efficient vitamin D metabolism, though supplementation would likely eliminate any real evolutionary impact. There's also the possibility of new mutations arising that change how skin pigmentation works. Evolution isn't just about selecting among existing variations. New genetic mutations happen constantly. Most are neutral or harmful and disappear quickly, but occasionally a beneficial mutation arises and spreads through a population. We've seen this with skin color before. The mutations that lightened skin in European and East Asian populations were once new mutations that spread because they provided an advantage. Could new pigmentation mutations arise in the future? Absolutely. We just can't predict what they'd do or whether they'd spread. Some researchers are also exploring the possibility of genetic engineering changing skin color intentionally. CRISPR and other gene editing technologies could theoretically be used to modify melanin production in an embryo, allowing parents to choose their child's skin tone. This raises profound ethical questions that society is nowhere near ready to answer. Should we allow cosmetic genetic modification? Would this reinforce harmful beauty standards or colorism? Would it create new forms of inequality? These aren't hypothetical questions anymore. The technology is advancing rapidly, and the conversations need to happen now. But setting aside deliberate genetic engineering, natural evolution of skin color will likely continue, just very slowly. And it won't follow the clean, latitude-based pattern it did in the past. Instead, it will be shaped by migration patterns, mate choice, random genetic drift, and whatever weak selective pressures still exist in a world where technology can compensate for almost any biological mismatch between skin color and environment. One thing we can say with confidence is that human skin color will remain variable. Even if average tones shift, variation will persist because variation is constantly regenerated through mutation and recombination. Siblings will continue to have different shades. Populations will continue to show diversity. And as long as humans live in different environments and maintain some degree of geographic or cultural separation, regional differences will persist to some extent, even if they're less pronounced than they are today. There's also the cultural dimension. Skin color isn't just biology. It's loaded with social meaning, history, and identity. These cultural factors influence who marries whom, where people choose to live, and how populations interact. And culture changes much faster than biology. The social meanings attached to skin color have shifted dramatically, even in the last 50 years, and will likely continue to shift in unpredictable ways. These cultural changes might have indirect effects on the biological evolution of skin color by influencing mating patterns and migration, but predicting these effects is nearly impossible. What we're witnessing now is a unique moment in human evolution. For the first time in our history, selective pressures that shaped a major physical trait have been largely overcome by technology and culture. And yet, the trait persists because evolution is slow and because skin color is still meaningful to us, biologically and socially. Where this leads is anyone's guess, but it's happening now, in real time, and you're part of it. The children being born today carry the next chapter of this story in their genes. So here we are, at the end of our journey through the biology of skin color. We've traveled from equatorial Africa to the frozen Arctic. We've explored melanin, vitamin D, folate, evolution, migration, and the beautiful complexity of human variation. And now it's time to step back and ask the bigger question. What does your skin color actually tell you? What does it mean? Let's start with what it does tell you. Your skin color is a biological record of where your ancestors lived. It's a map written in melanin, showing the intensity of sunlight your forebears encountered over thousands of generations. If you have dark skin, your ancestors likely spent significant time near the equator or in other high UV environments. If you have light skin, your ancestors probably lived at higher latitudes where sunlight was weaker and seasonal. If you have something in between, your ancestry might be mixed, or your ancestors lived in regions with moderate UV exposure, or both. Your skin color also tells you something about your body's current relationship with sunlight. If you have dark skin and you live in a northern climate, you're at higher risk for vitamin D deficiency and need to be proactive about supplementation or sun exposure. If you have light skin and you live in a sunny climate, you're at higher risk for skin cancer and folate depletion and need to be vigilant about sun protection and nutrition. Your skin color is functional information, a biological data point that should inform how you care for your health in the environment where you actually live. And that's it. That's what skin color tells you. It speaks to ancestry, to geography, to sun exposure, to nutritional needs. It's biology, elegant and adaptive, shaped by evolution to solve specific environmental challenges. But here's what skin color doesn't tell you. It doesn't tell you anything about your intelligence, your character, your worth, or your potential. It doesn't determine your personality, your talents, or your destiny. It doesn't place you in a hierarchy. It doesn't make you superior or inferior to anyone else, because in biological terms, there is no hierarchy. This is one of the most important lessons from studying the evolution of skin color. There is no best skin color. There's only what works best in a particular environment. Dark skin is superior at the equator. Light skin is superior in northern latitudes. Neither is universally better. They're solutions to different problems. And when the environment changes, or when you move to a different environment, the advantages and disadvantages shift. What was once adaptive might become neutral or even disadvantageous, and vice versa. Evolution is context dependent. A trait that's beneficial in one setting can be harmful in another. This is true for skin color, and it's true for every other trait humans carry. Height, body shape, metabolism, even cognitive traits like memory or spatial reasoning, all of these evolved in specific contexts and carry trade-offs. We recognize that height is adaptive in some contexts, basketball, reaching high shelves, and less so in others, fitting in small spaces, requiring less food. The same logic applies to skin color, yet somehow skin color got tangled up in social hierarchies that have nothing to do with biology. Genetic studies have confirmed over and over that there is more genetic variation within any given racial or ethnic group than there is between groups. Two people from the same African village might be more genetically different from each other than one of them is from someone in Europe or Asia. Skin color is controlled by a tiny fraction of your genome, maybe 15 to 20 genes out of approximately 20,000 protein-coding genes. The vast majority of what makes you who you are has nothing to do with melanin. And yet, skin color has been used throughout history to justify horrific injustices: slavery, colonialism, segregation, discrimination, genocide. People have twisted biology or invented pseudoscience to claim that skin color indicates deeper differences, that it reflects intelligence or morality or humanity itself. But every credible scientific examination of these claims has found them to be utterly baseless. Skin color is skin deep. Its pigmentation, its UV adaptation, that's all. So when you look at your own skin, or at someone else's, try to see it for what it actually is. It's a beautiful expression of human adaptability. It's a testament to the journeys your ancestors made across continents and millennia. It's a functional trait that connects you to the environment in ways you might not have considered before tonight. But it's not your identity, not all of it. You are so much more than the color of your skin. You're the cumulative result of millions of genes, trillions of cells, decades of experiences, relationships, choices, and moments that no melanin molecule can capture. And there's something humbling in understanding the biology of skin color. It reminds us how interconnected we are. All humans share a common ancestor in Africa. We all started with dark skin. The variations we see today, the entire spectrum of human skin tones, emerged in the blink of an eye in evolutionary terms. 50 to 70,000 years is nothing on the timescale of life on Earth. We are, all of us, one incredibly young species that's barely had time to differentiate. Our similarities vastly outweigh our differences. Every advance in genetics reinforces this. The Human Genome Project, launched in 1990, revealed that humans share 99.9% of their DNA. That 0.1% difference includes skin color, yes, but also hair texture, eye color, height, and countless other variations. None of it adds up to separate races in any biological sense. Race, as a social construct, doesn't map neatly onto genetic reality. It's a category we invented, and it's caused immeasurable harm precisely because we treated it as if it were biological destiny rather than cultural fiction. So, what does your skin color mean? It means your ancestors were survivors. They adapted to the world they found themselves in. They evolved the skin tone that allowed them to thrive under the particular slice of sky they called home. Whether that sky was blazing equatorial sun or dim northern twilight, they made it work. They survived long enough to have children, who survived long enough to have children, in an unbroken chain stretching back hundreds of thousands of years. And that chain led to you. Your skin is a gift from them. It's functional, yes, but it's also a connection to everyone who came before you. And in a world that's increasingly mixed, increasingly mobile, increasingly interconnected, your skin color is also becoming part of a larger human story, one where borders blur and categories dissolve, and we start to see ourselves not as separate groups, but as one endlessly diverse species sharing one small planet. Tonight, as you drift off to sleep, maybe you'll think differently about the skin you're in. Maybe you'll appreciate the biology behind it, the evolutionary pressures that shaped it, the nutrients it needs, the functions it performs. Maybe you'll feel connected to your ancestors in a new way, knowing that your skin tone is their legacy, written in melanin. Or maybe you'll just rest easier knowing that skin color, for all the weight we've placed on it socially, is biologically simple. It's adaptation. It's variation. It's beautiful in all its shades, not because any one shade is better, but because variation itself is what makes us resilient. Before you go, if you enjoyed this journey through the biology of skin color, take a moment to like the video. Subscribe if you want more content like this, and let me know in the comments what surprised you most tonight or what questions you still have. I love hearing from you. And remember, whatever shade your skin is, it's enough. It always was. It's perfectly designed for the journey your ancestors took and perfectly capable of carrying you through whatever comes next. Sleep well. Your skin is taking care of you, even now, in the dark. So, how does your day look now? You woke up this morning, probably without thinking about it, and your skin was already working. It was blocking UV radiation streaming through your window. It was regulating your temperature as you moved from your cool bedroom to a warm shower. It was sensing the texture of your clothes, the pressure of your chair, the warmth of your coffee cup. And all the while, those melanocytes buried in your epidermis were quietly producing melanin, calibrating your protection based on genetic instructions written over thousands of generations. We started tonight by asking a simple question: what is skin color, really? And what we discovered is that it's anything but simple. It's a biological masterpiece, a trait shaped by some of the most powerful forces in evolution: ultraviolet radiation, vitamin D synthesis, folate protection, immune function, migration across continents, adaptation to climates ranging from equatorial heat to Arctic cold. Your skin color isn't random. It isn't cosmetic. It's a finely tuned response to the environment your ancestors inhabited, and it's still functioning today according to that ancient programming. We learned that all humans started with dark skin in Africa, rich in melanin, perfectly adapted to intense equatorial sun. That dark skin protected against DNA damage, prevented skin cancer, preserved folate levels critical for reproduction and fetal development, and maintained immune function under constant UV bombardment. It was, and remains, the optimal solution for high UV environments. For hundreds of thousands of years, this was simply what human skin looked like. Then came migration. Small groups of humans left Africa and spread across the globe, encountering environments their bodies had never experienced. In northern latitudes, where sunlight was weak and winter brought months of darkness, dark skin became a liability. The melanin that had protected them so effectively in Africa now blocked the little UVB radiation available for vitamin D production. Children developed rickets, bones weakened, immune systems faltered, and so, slowly, over thousands of generations, populations living in these low UV environments evolved lighter skin, not because it was inherently better, but because it solved the specific problem of vitamin D deficiency in places where the sun barely shone. We explored the delicate balance between vitamin D and folate, two nutrients affected in opposite ways by UV radiation. Too much sun destroys folate, leading to anemia and devastating birth defects. Too little sun prevents vitamin D production, causing bone disease and immune dysfunction. Your skin color is evolution's answer to this balancing act, a biological thermostat set to the UV intensity where your ancestors lived. Dark skin prioritizes folate protection. Light skin prioritizes vitamin D production. Both are correct. Both are adaptive. Context is everything. We saw how the Industrial Revolution created a crisis of rickets among children in northern cities, revealing just how essential light skin and vitamin D are in low-light environments. We saw how fair-skinned populations living in sunny climates like Australia face epidemic levels of skin cancer and folate depletion, demonstrating the vulnerability of light skin under intense UV. We learned that modern life, with its indoor existence and technological interventions, has created vitamin D deficiency across all skin colors, breaking the evolutionary calibration that once kept us healthy. We discovered that skin color is far more complex than a simple gradient. It's polygenic, controlled by multiple genes that can recombine in countless ways. It's influenced by diet, hormones, age, and health. It varies within families, within populations, within individuals over time. Some populations don't follow the latitude rule at all, like the Inuit, who retain darker skin because their diet provided abundant vitamin D. Others, like Tibetans, have medium skin tones that balance multiple environmental pressures at high altitude. The spectrum of human skin color is continuous, overlapping, and infinitely variable. We learned that melanin does more than just block UV radiation. It has antimicrobial properties. It protects immune cells from sun-induced suppression. It preserves the collagen that keeps skin strong and youthful. It's chemically active, neutralizing free radicals and toxic metals. Dark skin is a multi-layered defense system, and every layer matters in the environments where it evolved. We explored the question of temperature regulation and discovered that skin color plays almost no role in keeping you hot or cold. Thermoregulation is handled by sweat glands, blood flow, body composition, and behavior, systems that work equally well regardless of melanin levels. Skin color is about UV management, not thermal management, a reminder that evolution optimizes traits for specific functions, not general superiority. And we look to the future, recognizing that evolution hasn't stopped. Skin color is still changing, still responding to new pressures, though those pressures are now more cultural and technological than environmental. Migration and intermarriage are blending populations, creating new combinations of skin tones. Modern medicine and supplementation have weakened the selective pressures that once drove skin color evolution. Where this leads is uncertain, but it will certainly be different from the past. Through all of this, one truth has remained constant. Skin color is biology, not destiny. It tells you about ancestry, about geography, about nutritional needs and health risks. But it tells you nothing about intelligence, character, worth, or potential. The science is unambiguous on this point. There is no biological hierarchy of skin colors. There is only adaptation to different environments, and adaptation is always context-dependent. So tonight, as you settle into sleep, I want you to carry this understanding with you. Your skin is not just a covering, it's a story. It's your ancestors surviving under skies you may never see, adapting to sunlight intensities you may never experience, passing down genetic instructions that still protect you today. Every shade of human skin exists because it worked somewhere, for someone, long enough to create the next generation. That's not hierarchy. That's diversity. That's resilience. That's the genius of evolution playing out across continents and millennia. And here's something worth considering as you drift off. Sleep itself is connected to the biology we've been discussing tonight, vitamin D, which your skin produces from sunlight, influences your circadian rhythm and your production of melatonin, the hormone that tells your body it's time to rest. When your vitamin D levels are low, your sleep often suffers. You might struggle to fall asleep, wake frequently, or feel unrefreshed in the morning. This is your body signaling that something is out of balance, that the ancient relationship between sun, skin, and rest has been disrupted by modern life. So if you've been struggling with sleep lately, consider whether vitamin D deficiency might be playing a role, especially if you have dark skin and live far from the equator, or if you're like most modern humans and spend almost all your time indoors. A simple blood test can tell you where you stand. Supplementation is easy, affordable, and often dramatically effective. It's one of those rare cases where modern medicine can perfectly compensate for an evolutionary mismatch between your biology and your environment. Before we end tonight, take a moment to appreciate the skin you're in, not because it's better than anyone else's, but because it's yours. It's functional, adaptive, and beautifully suited to the journey your ancestors took. It's carrying their legacy in every melanocyte, every molecule of eumelanin or pheomelanin, every genetic instruction refined over countless generations. You are the latest chapter in a story that stretches back to the very origins of our species. If this journey through the biology of skin color resonated with you, do me a favor, like this video, share it with someone who might find it interesting. Subscribe if you want more content exploring the beautiful, surprising science of being human. And leave a comment. Tell me what surprised you most tonight. Tell me how you're thinking differently about your own skin. Tell me where you're tuning in from and whether you've ever thought about how your skin color connects to that place. I read every comment, and I love hearing from you. And here's a challenge, if you're up for it. Tomorrow, when you look in the mirror, see if you can see your skin differently, not as something to judge or compare, but as biological engineering, as evolutionary history written in pigment, as a connection to ancestors who survived impossible odds. Your skin is enough. It always was. It's perfectly designed for the world your ancestors knew, and it's carrying you through the world you know now. Rest easy with that knowledge. Sleep well, and remember, whatever shade you are, you're part of one beautiful, diverse, endlessly adaptive human family. Good night.